So still in other projects? Still breathing? Yeah, different projects. Perspective I have on it is very ordered right now. I've been looking at those estimations. So, taking inputs from RGB cameras or RGB depth cameras and estimating the frequency. So that's the literature I don't know exactly what the driving so it's just experience from this class. So all the best solutions are straight up. And like there's lots of different solutions. There's pretty good data sets. For example, the recent model was actually published earlier this month that does 2D, 3D pose estimation and does activity later. So like isolate everything yeah, and it's pose estimation from still images or video, right? And so yeah, it's definitely interesting. Yeah.
Oh yeah,
Okay, let's get started. Hopefully, the last couple of days, last couple of lectures weren't too bad. I missed you guys. Maybe you missed me, maybe not.
You did.
Dave Healy, who's here on Tuesday, is a good guy, good friend. Hopefully he filled in the gaps there. And then Alessandro, is he not here today? And he's filling in on Thursday. That was good. So, scores came back on the homework. Tom V has been diligently grading those and got those back. And whether your score was good or not good, or what you hoped or not, really appreciative to Tom V for all the hard work on that. She's offered to answer questions about that, and I don't know if you want to say anything more about that.
no, nobody came to see it. I got a few messages on that, and it was pretty happy.
Okay. All right. The other homework is out. Hopefully you got that announcement over Canvas, and yeah. If you looked at it, you see that it's a little bit like continuing on with what we were doing in the last one, where you're actually writing code to understand some of these more important parts of neural networks, in this case convolutional neural networks, and then actually using TensorFlow to train some pretty simple convolutional networks. So yeah, I'm always happy to answer questions on those, and so are the TAs. So just let us know. All right, let's get started. Okay, so today, it took 3 lectures to do the history of convolutional neural networks, and was only planning on 2, so this week was supposed to be 2 lectures on visualizing and trying to understand what convolutional networks are actually learning. We're going to jam it all into one day. That should be okay. This is mostly just like a fun lecture, just looking at the tools that people have developed to understand this thing. So I think we should be able to get through it all, and then we'll be caught up with the syllabus. So the question we're asking ourselves is, okay, so these networks they've been trained. Here's AlexNet, been trained on on ImageNet, and it's got this great score. It does, it's able to classify these 1,000 classes really, really well. That's awesome. We're really excited about that because we're excited about classification. But then the deeper question that people wanted to ask and want to understand is what's really going on inside of these networks. Like what is it like? Okay, so we know it's learned to do really well in the classification problem. But what has it learned along the way? Like what's how can we go about understanding that? In particular, we have many layers of convolutions. Like what's being learned at each of these layers of convolution, or say, like what's being represented there. So we're going to spend the day kind of thinking about that. So we've seen a little bit of this already. It's pretty typical that to ask the question, okay, what was learned in the first layer? And almost always the same answer comes out. You learn what are called Gabor filters. And Gabor is a name, so it's capital G, Gabor. I'm not really sure why it's associated with that person's name, but these are all like edge detectors, basically. So if you take a look at these, what's being shown here, so these are like the 11 by 11 filters from AlexNet, and then the 7 by 7s and 2 different depth ResNets, and then a DenseNet, which I think was probably touched on just briefly in the last lecture. But anyways, the point is that, just visually you can see that these are basically they all have kind of the same character. They're these edge detectors. They're either like a straight, like a linear detector, they could be at any angle, or there are these like radial detectors. So it's another kind of edge detector, but just like, radial in the sense of like you're detecting like the edge of a circle. And you see the different like color patterns, so you can recognize these things at different, for different colors. Because remember, there's 3 different color channels as the primary input here, but that's what you get. And no matter what you do, this is basically what you get. So yeah, it's cool to know that, but it's not really like helpful in terms of understanding what's really being learned here. Just if you don't get this, something's gone wrong probably. If you're training on like natural images, like natural scene images, like ImageNet. Like when we train on cellular images at Recursion, we get somewhat different initial filters, but they're all edge detectors. You can ask about like the outputs of, or like just look at the raw filters themselves at every layer, but usually it's pretty hard to interpret it. And it's even harder in a slide like this where you can barely see them. But the point is that as you look further, they get more and more abstract, and it's really just looking at them, it's hard to understand what's going on. So we don't typically do this. We don't typically go to like the 5th convolutional layer in the network and look at the filters that were learned there and say, oh, that's what was learned. Because there's not really like a simple way of interpreting that. So what do we do instead? Well, one thing that's done is, many of these networks have these last layers are fully connected. So that you have these dense, fully connected layers after convolutions. So like AlexNet's got a couple, ResNet's got 1. So you have these things. What's nice about them is it's like you've gone from like the spatial feature maps, so they have like this width and height dimension tuning, but then that gets all collapsed down into like a single vector in some high dimensional vector space, and so what we can do is we can start to just like use those vectors and ask like vector questions, like geometric questions, like within that space, what do these things look like? Mostly what we ask are like, what's nearby these things? So like, again, if you put an image into the, give an image to one of these networks and run inference, which is basically the process of running the forward pass on that image through the network. You get some numbers at that final layer, and you say, oh, well, like that's a now, even though 4096 is a high dimensional, is a large number, and that's a high dimensional space, it's much lower dimensional than the original pixel space. And we might ask, like, what can we understand by just thinking about what's going on in that vector space? So, here's the kind of thing that you would typically see. So, we start with an image like this purple flower up here, and we embed it in this network and run inference. We get out its final embedding, this 4096 dimensional vector. And we do that for all the images, and we say, okay, given this one, give me all the nearest neighbors. So like this one, we're picking like the L2 distance, like just Euclidean distance between the vectors. You can pick any sort of distance you want, but you say like, what other images are close to this? And lo and behold, you get a bunch of purple flowers. And you start with an elephant, and you get a bunch of elephants. You start with a battleship, and you get a bunch of battleships, and a jack-o'-lantern, and so forth. This is really cool, right? Because what's happened is, like in pixel space, these things aren't necessarily near each other. In fact, if you remember way back to the beginning, we were thinking about just like linear classifiers on images. And we looked at nearest neighbors just in the pixel space. This is kind of blurry looking at it like this, but like, here's this frog, and the nearest neighbor was like a cat, and the second nearest neighbor was a frog. But it wasn't always that like it's like something semantically meaningful as the nearest neighbor. But here you are getting that, and that's because what it's learned to do, right, is to basically take this image, transform it all the way to this final layer, and then use that final representation, and uses that to do the softmax classification. So if it needs to, classify purple flower, which actually isn't one of the classes, but elephant or whatever, all of these things that are of that class, they have to kind of be near each other, so that when it's given to the softmax, and that dot product happens between the representation for elephant and the representation that's coming out of the final layer here, like those things have to basically match, so that the dot product is large, so that the probability assigned to that class is the highest amongst all the other ones. So this is cool. Like this is really, really useful. We are just by the process of learning to classify these things, we're transforming these images into vectors that preserve some semantic meaning through the geometry of the space. So things that are nearby, nearest neighbors, are like each other. This is just a byproduct of the whole way that we train these things, and the fact that we use softmax to do the classification. So cool. People use last layers for and even like penultimate layers, like the last layer of penultimate, and maybe combine concatenating those as like representations of images, lower dimension representations of these images, and you can do all kinds of great things with them. But that still doesn't really like bring a ton of meaning. Here in this slide, we're projecting all of those images, projecting them into 2 dimensions. You can do that through whatever dimension reduction method you want, like PCA, or use something like TCE, which is either in favor or out of favor depending on the week. And you can see that like basically you get clusters of things. So you can even take this really far. This is cool. So Andrea Karpathy took all the images from ImageNet and basically like embedded them in one, like laid them out in one 2-dimensional space where nearest neighbors are all near each other. So you can kind of see like some local structure within ImageNet. Like this is great, but it's not super useful because it doesn't really, like in and of itself, it doesn't really give us a semantic meaning. It just says that like if 2 things are near each other, then semantically they should have something in common. It doesn't really say like, I can look at this thing and say, oh, and I can infer that that's the representation of a dollar or something. You can do this at other parts of the network as well. If you remember, we did this. We watched this video where Jason Musinski is describing, some ways of trying to do exactly what we're talking about today, understanding convolutional networks. And basically here, he's plotting all of the 128 13 by 13 feature maps in the convolution and the Com5 layer of AlexNet trained on ImageNet. And you remember he was showing that, like, in this feature map, we're seeing neurons that are activating for his face, and he showed the thing about the wrinkly clothes and things like that. So that's like another way of going about this, but it's pretty cumbersome to kind of like search through everything, but pretty cool. So what are some other ways that like don't require us to just like search through everything, but to sort of like we expect it to give us something meaningful? So here's something that's done. So maximally activating patches. So the idea is like you just pick one neuron. So you pick a layer, you pick a neuron in that layer, a unit within that layer, and you run inference on all the images, and you record all of the activations at that neuron. So all the outputs of that neuron, and then you say, okay, for which of these? So you take like the top. All the images that made that neuron most active. So like the top the images that activated that neuron the most, and you just take a look at them. So in this picture up here, like the tops, those 6 top rows that are separated from the other ones right down here, those are 6 different neurons in this Com5 layer. And you can see like in that top one, like there's something very common. There's like this center kind of dark dot. And this usually looks like an eye of an animal or something like that. You can see like in the 4th one, letters are a common theme there, also with the 6th one. You can see like in the 2nd and 3rd row, there's like a sort of an orientation of an edge is there. So by looking at these things, you can visually look at these things and say like, what's common amongst them? It's like, oh, that neuron's learned to, it's activated when there's like an edge running from the upper left-hand corner to the bottom right-hand corner. Something like that. It's also pretty cumbersome, but an interesting way to think about these things.
So are those images on the slide from the input image, or are those actually the filters they got?
No, sorry, yeah, these are the input images. Yeah, so these are the images that are activating a particular neuron the most.
Oh, okay.
Right, so each row up there is just like picking out one of the neurons from the 5th convolutional layer in this AlexNet, and just saying, when I run inference on all of the images, and I just record whatever the activation is, whatever the value of that neuron is when we run inference, and I just look at the top 10, the top 10 highest values. Those are the images associated with it.
So it just shows us what the neuron's receptive to.
Yeah, like what the neuron is, receptive to. What the neuron is like has learned to be active for.
So kind of confused how you get the certain, well, you can see that that's the picture, but how do you get the eye itself, like that small segment of the picture?
Oh, like the fact that it's cropped?
Yeah.
Yeah. So, this is in combination with the receptive field of the neuron. So every neuron is only seeing a certain portion of the image. So depending on the architecture, and where you are within the network, all the values that are contributing to the activation at that one neuron, you just keep looking back and just depending on the architecture, it's some patch. It could be the whole image, but frequently it's not the whole image, especially in these more shallow networks. It's usually a much smaller patch. So like this is the receptive field for that particular neuron. Yeah, good question. Yeah, so this is like some way of thinking about how what things are learned, but it's also again pretty cumbersome. Okay, so let's think of even better ways of doing this. So, yeah, this is also cumbersome. So we're going to start talking about saliency, but we're going to first motivate this with occlusion. So we have this image that is classified as an elephant, it's clearly an elephant. What you can do is you can do things like, you can ask yourself, like, which pixels are most contributing to, like in this entire image, most contributing to us determining this is an elephant. So what you can do is you can take, like, you know, some random patch within the full image and set those values to something like, in this case, constant. Just make them, you know, make them constant so that really there should be, like, hopefully you would imagine, like, very little value coming from these newly assigned pixels in terms of determining the probability of this being an elephant. So you can see in this sort of contrived example, you know, and you would expect this, I suppose, that if you were to occlude the pixels off the elephant, so like here on the ground, you would expect that to not really contribute, at least you'd hope that wouldn't really contribute to assigning a high probability to this being an elephant. Because it really has very little to do with an elephant. I mean, it might be the case that all the elephant pictures, the elephants are walking on dirt, and maybe it does contribute a little bit. And it would be interesting in this contrived example to know exactly what the probability was and, like, what this dropped, you know, what it dropped to, but I don't have that here. But more importantly in this example is, now if I include the pixels around the face of the elephant and, like, a big part of its ear, the probability that this is an elephant drops significantly. You probably still classify this as an elephant. You know, if among 1,000 classes you've assigned this 0.75, well, it's going to be your highest probability. So you're still going to assign this to be an elephant. The point is that, like, probability of it being an elephant dropped quite a bit. And you can imagine, like, making this occluded region, like, larger and larger until basically this doesn't recognize it as an elephant anymore. You know, this is like useful because it's useful to get some understanding of, again, what pixels, what parts of the image are really contributing to the classification here. But again, pretty cumbersome to sort of, you know, come to some kind of understanding of that. So, yeah, just other ways of looking at it. So here's another idea how to do this. This is what's called saliency. So salient being, you know, something like, you know, referring to, like, things that are most important. So the way that we compute saliencies, there's many ways to do this. This is how you do this via backpropagation. So you take this image of a dog, and you'd expect that when you run forward inference on this, that you would get, you know, the high probability being being a dog. So this, you know, this learned to classify this as a dog. Okay, so, like, what parts of this image is this network really using to classify this as a dog? Well, what you can do is you can take the score associated with dog. So remember, the score is like the value coming out of the linear map at that final fully connected layer before you give it to the softmax transformation to turn it into a probability distribution. So you take that score and you compute the gradient with respect to the image pixels. So, like, yeah, so this is respect to, so we're computing a gradient of that score with respect to each of the pixels within the original image. And yeah, and if, in this case, what they did was to, you might get positive or negative values of that gradient. So again, we're back propagating from that score all the way back through, all the way to the image. We might get positive and negative values, so what we do is we take the absolute value of that, and then we have 3 channels of color, so, like, just kind of simplify and get an understanding. We actually just take the maximum value of that absolute gradient at each pixel. And what we see is the black is, like, 0, but anywhere else that it's not black, this is some non-zero gradient there. And so what this is, you know, should suggest to you is that the pixels surrounding the dog are the ones that are contributing to this being the score. And I mean, that's pretty cool. I mean, we would expect that to be the case, but, you know, it's not clear that that should have been the case. if you think about like what's happening, you were just doing linear transformation, Rayleigh, linear transformation, Rayleigh, Max Cooley, But it turns out that yeah, it has learned to, when classifying this thing, has learned to focus in on these pixels. That's pretty cool. And an interesting use of the idea of gradient. Why do we use gradient to like look at this? Why should this work? Back propagating the score for dog here. Yeah.
So you're just saying that it has some effect on the classification process? Is that too simple of an explanation?
Well, no. I mean, it's along the right lines. So, yeah. So, like, when we compute the gradient of the score with respect to the pixels, what is that saying? What's the gradient telling you? If I want to make this score higher for dog, what should I do? Yeah, I should walk up the gradient, right? I should walk up this gradient, the gradient of the score for dog with respect to the pixels. So what this is doing, this is picking out the pixels within the image where, like, if I walk up those, if I can sort of amplify those, I get even a greater score for dog. So that's like the intuition behind why this should even work. Is we're using gradients. We're using that signal that says, make this more dog-like. And yeah, notice that it didn't like go over here and say, yeah, I don't know, do something over here, because like you could do something over here. You could change the pixel over here and make another dog. But that's a really big, huge change from like where you are, right? This is like, remember, the gradient is just like some local information. Where if I'm standing at this image, in which direction can I move? It's some infinitesimal move to make this more dog-like. So anyway, that's the intuition, and we're going to use these ideas of gradients basically through the whole rest of the lecture today to be producing these understandings of what's going on in the networks. Questions so far? Okay, so here's some examples of other saliency maps. So, this was classified as a boat, so let's look at the gradient of the score for boat with respect to those pixels, and we see that like the boat, especially the sail is highlighted, and it looks like also the water is being highlighted here. We saw the dog already. Some crazy fruit. I imagine that's what that is. Car, fish. So what do you recognize about in all these examples? Whatever the category is, it's basically learned to highlight it. And it's not like perfect, but it does it pretty well. And it actually turns out that if you start with these maps, these saliency maps, and you sort of enhance them and do some basic like image segmentation stuff. So what's like graph cutting algorithms, if anybody's ever worked on anything like that. What happens is that you can actually cut. This typically happens. If this was classifying Grasshopper, and we do this saliency map for Grasshopper, and we enhance this image a bit, and we do the graph cut, then voila, we actually get that we can cut the entire Grasshopper basically out of this pretty complicated image of Grasshopper plus leaves and stuff. And again, the snake, you see just the snake parts. There's a little bit of sand right here, whatever the floor is on this here. That would be a kind of a hard thing to cut out given the method. I don't know what kind of bird that is, but this bird, that's pretty awesome. Think about it for a second. All we said when we were training this thing was there's a grasshopper in this image, or there's a snake in this image, or there's some funky bird in this image. That's all we said. We didn't say where it was, we just said it was there. We saw lots of examples of birds and grasshoppers and snakes and whatever. But as a result of learning to do this classification, it has learned basically where that object is within the image. That's pretty amazing, actually. I think that's actually incredible. It's what you'd expect, but this is like really hard to do. Try like people have been working, you know, to do this kind of thing for decades, and you know, very sophisticated algorithms. Of course, this is a very sophisticated algorithm, but it's just a byproduct of it that we can get this kind of segmentation. So pretty cool. We can do this in, we don't just have to start with the score for the class. We can do this procedure for any feature, so for any neuron in any layer, and get it back. Oh yeah, I'll get that in a second. So what I told you is kind of like the standard way for computing a saliency map. There are some like tweaks on that are called deconvolutional networks. And the basic idea is you only backpropagate positive gradients. And if you do that, what you get are these images. So it's basically, these are like the same saliency maps we were just looking at, but you're only backpropagating positive gradients. So they sort of, you know, like when we were looking before, it was like this cloud of, let's see, you know, it's like these clouds of points here. And those are great, those give us a lot of understanding. But if we do this, we only backpropagate the positive gradients, then we get these kinds of things. So very similar, and maybe like a little bit like visually like easier to interpret, I don't know. At least it's not just like a cloud of points, like you can see that what it's doing, like on this, you know, you can actually see like the E and S, or you can see like the noses or eyes up there, or the edges, or whatever. And again, what this is saying is, if I were to start with this image, and I were to make some change in these directions, as described here by these maps, then I would increase the, you know, the score, the activation, or whatever neuron I'm looking at. So someone just figured out that, like, hey, if we only backpropagate positive gradients, then we get something that looks like this, and maybe that's useful. Yeah, what's cool about this too is that, like, you can see, like, yeah. So this is now focusing in on neurons within convolutional. This isn't like necessarily the final score. This is like looking at activations of neurons within some intermediate layer. This is cool. Like, you can see that, you know, some of these things are activating for like the whole face of the dog, or like the circles, and you can get like these more, like, far more complex, or yeah, far more like these richer understandings of what is happening, or what these neurons are really activating. Okay, so another technique for going after this kind of understanding is to use gradient ascent. So in backpropagation, what we're doing is we're saying, okay, we have this original image. You know, we pick some neuron, you know, usually like the score for a class. We backpropagate, and it's telling us, the backpropagation is telling us, like, in which way we should shift the image to make it even more, you know, to activate that whatever neuron we're focusing on even more. We can do this. We can do something different using gradient descent. So what we can do is we can use gradient descent to, like, start from like a random image, and then we can walk up gradients that are, again, are determined by, like, how to maximally activate a neuron, and adjust and do this iteratively, kind of like backpropagation, but we're actually walking up a particular signal. We can adjust that random image until it looks more and more like it's every time we make a step, it's activating that particular neuron of that particular class more and more. And if we do that a number of times, then we get some sort of image, and we can look at that and say, like, what did we learn from that? And there's two pieces to this usually. It's like, you know, like we're trying to, like, activate a particular neuron's value of the activation. And there's typically a regularization term in this that like tries to produce more natural features. Because again, we're starting from some random starting point. So, or a zero starting point. So yeah, this is just like a slide saying what I just said. We start with something random, or in this case, this example, 0. We do a forward pass in the image to compute scores. We do back propagation to get the gradient, but we walk up the gradient in this case to change this image to look to be adjusted in the direction of activating that neuron even more. So what comes out of this? Okay, so strange things come out of this. So again, starting from like 0 or random, I really don't know why these examples, but dumbbell, right? So like you know, I iterate this process and I keep walking up these gradients that are making this image look, you know, be more and more active for dumbbell, and I get this like very strange thing that's got like 6 dumbbells sort of like continuously connected to each other. Same thing for any of these. The cup, bell pepper's funky, right? It's like a bell pepper's thing here and then there and there and there. Dalmatian is scary. So these are kind of weird, but like, what's interesting in these? Remember, we started from a random image or like a 0 constant image, constant pixel values. Does it surprise you that like the thing is showing up? Like, remember, again, like these don't really know, these networks don't really know what a dumbbell looks like. At least you're not telling it. I mean, you're giving it examples of dumbbell or cup or lemon or bell pepper or husky or dalmatian. You just, you know, it's seen a whole bunch of examples of this, and it's learned, and you can see this, you know, this learning as the signal determined by the gradient. It's learned to say, okay, well, like if I'm going to be, if this thing is going to be more Dalmatian-like, then it needs to kind of like look more like this. I mean, it's cool. Like, it's cool that it actually does something that, like, visually is meaningful. You can play with these things all day, and you could really spend way too much of your life doing this because it's sort of fun. It's like kind of psychedelic, right? I don't use drugs, but I imagine if you were like using some sort of drugs and watching these, this would be exciting. It turns out you can make these even like more visually appealing to look at, says the guy who's making these. Maybe it's high or whatever. You can apply like certain types of image. So you can kind of blur the image as you go. You can clip the pixel values so that they're not too small or the radius not too small. And you run the same process, but just kind of having a little bit of this extra care to it. And you get things that look even more like the images that you'd expect to see. So, you know, there's like, those look like flamingos and pelicans and ground beetle and an Indian cobra. Yeah, so like doing a little bit of massaging along the way gives you things that look even more like what we expect to see. At least, you know, like the Gaussian blurring is making it so there's just not some jarring like transitions in the images. And yeah, the clipping is just so that there's still some signal. Like I said, we just keep going. We could really waste a lot of time doing this. Yeah, and you can, so all those examples were for, obviously for the score since we had a label for them. But you could pick any neuron in any layer and do these things. And you get some sense of, again, what that neuron is looking for, what it's activating for. So like, you know, here's some of the sort of maybe eye-like things up here. This one's troublesome. It's like a spider of some kind. This one likes to see spiders. I don't know. Some of these are like, you see this. It's really interesting to see this too. Like, we know at layer 1 would be those Gabor filters, those edge detectors. But as we move up in layers of abstraction, you can see that these are a little more complicated type of like geometric shapes, and these are even more complicated geometric shapes. And now we're getting some like swirls and like many curves with many transitions and things like that in them. Freaking spider or things like that. So it's cool. Like I would call this like, oh, I know what's going on in this network, but it's interesting to kind of get some understanding of what neurons are activated for in their receptive fields. This notion of receptive field again is really important. Remember that like at every layer we're getting these feature maps. As we apply a filter and we convolve it with whatever is the feature map, the output from the previous layer, and we run this convolution, we're getting this new feature map. And what was I going to say about that? Oh, the receptive fields. So, as that filter is like moving along and moving around, it's convolving stuff that each of these neurons that has its own receptive field, so that together they all have like some joint receptive field. And again, like what this is saying, like a neuron in any one of these layers is like in its receptive field. If it sees something like this, it's going to become very active. It doesn't mean that the whole image has to be like this. It just means like if it sees something close to this, it's going to become active. And again, you're building up this kind of hierarchy of like visual complexity, so that you can respond to more and more complex images and things with inside. Yeah, you can continue to do this. Question.
So it's kind of an observation, maybe not useful, but like we're used to seeing the images and seeing the direct thing, but these remind me of like introspection of like I'm trying to imagine an object, and we don't store a permanent two-dimensional map in our heads. We just have.
Yeah, that's an awesome comment. So like a lot of people kind of think along these lines. It's like, these networks are loosely based on what's going on in our own heads, and this gives you some understanding of like what. Again, like this is the thing that a single neuron within this whole network is responding to. So like, I mentioned like this idea of like grandmother cells. Like it's possible that there's one cell within your brain that when it sees, when your grandma comes into your into your visual field, it starts firing. It's like grandma's here, or whatever. Maybe yours is like food or something. Like, oh, look, food's here. But it's like that seems kind of crazy when you like think about it. Just like how can my brain work like that? But when you look at these, you start understanding what's happening here. You think, oh, maybe our brains are so complex that it can actually build up a neuron, out of all these layers of abstraction that is like the grandma cell. This has been observed in experiments, but apparently you have like neurons like this for like all famous people that you recognize. Like there's like a neuron for like Brad Pitt, there's a neuron for Donald Trump. It's pretty crazy. Yeah, these can just keep. These are. Again, I'm like stopping and looking at these. Going, wow, the jack-o'-lantern one is like freaky, right? Yeah. Everything you're seeing here is like. So this is like this one right here is slightly different from what we've been seeing, and this is instead of optimizing all the way back to pixel space, this is optimizing in one of the fully connected layers. And so it's like you instead of adjusting the pixels in the original image, you're adjusting the values in one of the earlier fully connected layers in this AlexNet, and you get things that like a little more even like dreamlike here. Like look at this pool table. Like that might be something that shows up in your dream. I don't play pool in my dreams, but it's got this really interesting quality to it that reminds me of like kind of dreamlike scenes. But who knows? That cloak one up there is like, things are like scary in here too. Actually, I mean this seriously. Like, it's weird. It's weird that like when we do this, we see things like this, and it's like to me, I look at that and I'm like, oh, like I associate that with being scary. And like, all it is like, hey, we've activated, like we've optimized for a certain class in this neuron or in this network. It's cool. Okay, here's something else that's really interesting. It's a huge area of research because it's really sort of troublesome. Maybe you've heard something about this already, but adversarial examples. So using these same ideas of like walking at gradients that help you to classify an image better, you can actually start from like a particular image that's clearly classified as something, and you can take that image and then you can so instead of starting from a random image, you actually start from like a recognizable image. It's something that the network knows how to classify well. And then you start applying this gradient descent method, and you start changing the pixels of it, and then all of a sudden you can get it to switch over and start classifying that image as this other thing. And you might expect like, wow, it's going to like really take this elephant and turn it into like a weird looking dog or something, but actually it doesn't. It doesn't need much to actually trick these things. So this thing clearly is an elephant, right? And it gets classified as an elephant. But then if we start with this image and we say, okay, let's make this more koala-like by computing gradients and walking up the gradients in the direction of koala. Like if I look at those two things, especially on this crummy resolution, like those two things don't look different from each other at all. This is the difference between them, and you can barely tell the difference between them in this image. And here's it magnified 10 times. But it thinks this thing is a koala. So that's really bad, right? That's really bad. That is not a koala. It's not even close to being a koala. Here's a boat, and you want it to look like an iPod, and you don't have to do much to it to make it look like an iPod. So these are called adversarial examples. So much research going into this, because like this is probably one of the most troublesome aspects of these networks is that they're not robust to these kinds of adversarial changes. Now, you can't just add noise and get something else. It's not. This isn't just like white noise that you're just like Gaussian sampling and just adding to it. That's not what's happening. You are making very specific changes to the image that are making it look more and more like whatever is the chosen class. So it's not just like a random behavior, but you can walk in these particular directions away from the image in this pixel space and immediately get something else. Yeah, we were like so excited about these things, and we saw this and we're like, oh man, like, what are these things? Well, remember, all it can learn is what it sees in the training set. That's all it has, right? And it's got like 1,000 examples of an elephant, and another 1,000 examples of koala. And I mean, we can definitely tell the difference between. Like, we know that this is not a koala, but the network doesn't. So maybe we've had a lot more experience that allows us to do that. I don't know. This is where some of the analogies between the intelligence represented here and human intelligence is quite different. But yeah, this is really troublesome. Yeah, there's a great lecture on this. I linked it out to you. Okay, so now with that trouble stuff behind us, let's actually hallucinate for a little bit. Oh yeah, question.
Shouldn't data augmentation somewhat regularize against that? Like,
Does data? No, it doesn't, right? Because like these were trained with data augmentation. Yeah, like that. So these are some of like the techniques for trying to protect against it. Is like make these kind of very specific changes in those directions. But the trouble is that like there's 1,000 classes, and you can't like augment the data times 1,000. Like it's just too much data, and you don't really know which direction up to change it anyways until it's converted. So it's like a very slow process. But your intuition is right. You could give it these examples and say, hey, this is not a koala, this is this is an elephant still. Okay, good question. Good comment. Okay, so like I said, let's hallucinate. So, so there's this like related technique to this, to what we've been doing, that is done in this way. It's called, it got the name of deep dream or Inceptionism. So we start with an image. So here's just like this very serene blue sky picture. And we just start with any layer within our convolutional network that's learned and classified on this sky or whatever. Actually, this doesn't have to be some recognizable thing. We can start with we can start anywhere. And then so we pick some layer, and then we do a forward inference, and we compute the activations at this layer. So all the activations at this layer. And then what we do is we set the gradient of that layer to the activation. So instead of actually doing the back propagation here, we just take those activations and we use that as a gradient. So if you think about that, what that's saying is like it's reinforcing the activation. So anywhere that was really active, that's going to be like a large gradient. And we use that for back propagation, and we update the image like we've been doing. And so what happens? So like again, this is like a train network. So think AlexNet trained on ImageNet. Now we just get through anything. So this image of the sky, and we do this procedure where we use the activations of the layer as the gradient. So we're like, whatever's being represented in that layer, we're gonna like, if any of it sort of exists in this image, this iterative process is going to bring it out. It's going to amplify it from the image. Okay, so what's going to happen here? All right, so here's the original image. So here's using, I think, the COM5 layer of AlexNet, and iterated, I don't know, 20 times or something like that. Like, look at that. Is that not weird? Like, what are you seeing here? Yeah, there's like the most bizarre animals ever. There's like a city, yeah, and it's like not just a city. It's like this is like some like I don't know. It's like a tower with like a dome on it. Like what? This is what a neural network. This is a neural network hallucinating. Honestly, this is like there are some mathematical theories about like geometric hallucination, which are very similar to kind of like the process being done here, which is like you perturb neurons in the visual, like in V1, so like primary visual cortex, and you get geometric patterns, which early on in your visual system, those are the kind of things that should be learned or should you're activating for. This is up much higher. You learn like crazier things. So it turns out that like these things are given names.
Who names these?
Well, people who do them for the first time. I mean, they're like if you were to go through some names, you'd probably name them something similar, right? Like this one's sort of strange. I don't really know where Admiral Dog comes from. There's like a dog-like thing with I don't know, like a helmet on or something. This one's clearly a pig snail. Like there's just nothing. There's nothing else that it could be. Snail, there's a pig. Camelbird, dogfish, yeah. Yep. You take any image. You take an image of yourself, and you do this procedure with this layer, and you're basically going to get like pig snails and camelbirds and dogfishes. Maybe not the exact ones, but they're going to come. And the whole city's going to come out. And this is at a lower layer, so we haven't learned, like this layer doesn't represent as, like these abstract notions of like dogfish. This is learned more like textures and shapes and things like that. So that's kind of cool, huh? It's pretty appealing. I like looking at that. Like I said, wasted way too many hours. Yeah. You can just like, if you just kind of keep iterating this procedure, just keep going and going and going, like, yeah, you can get some really funky stuff. It's like heaven, right? It's like, like these beautiful buildings made of gold, and you're greeted by, I don't know. Yeah. Woo! Maybe it's hell, I don't know. But fortunately, they have two-wheeled machines there. Yeah, you can just play around with this a ton. And like, there are web pages you can go to and give it images and it produces stuff for you. And it's not hard to go pick up code, and the stuff exists for most of the code exists for most of the deep learning frameworks to like run these kinds of procedures. So it's really pretty cool. Okay. So what other kinds of crazy things could we do here? We're not done yet. We got lots of crazy things we could do. Okay, so here's a procedure called feature inversion. So if we start with some trained network, like what we were just using, and we embed an image to some layer in the network, we can do the following. We can start with that, like that layer. We can say, okay, I want to fix that. I want to fix that representation in the network, but then I want to backpropagate and change the image so that it looks more natural. So basically, like we're just regularizing it so that we get more smoothness. And it kind of seems weird. It's like, okay, what would you expect to happen here? So you get like this kind of thing coming out of it. So if I fix what's going on in early on in the network, this is the radio after comp 2 and the VGG 16. Then I don't really see much difference in the image. But notice that as I go up higher and higher into higher and higher layers, the thing that is produced that looks most natural at that layer is totally different. It's totally different. You're getting something that's this is looking more like paint, artistic, right? This idea gave rise to something very cool. Oh, and along with this idea, but it gave rise to something very cool called style transfer, which we're going to look at in just a second. So, texture synthesis. So, it's not hard to imagine, given some sort of almost periodic pattern like this, to create an entire surface having that same pattern of texture. It's a pretty easy procedure to do. Just sort of move line by line and just produce the thing that you should using the pattern as some sort of base patch. You can take this and go a long ways. So here's some sort of larger image that has some sort of almost periodic pattern. You have these rocks on it's on a mountainside, maybe it's at a beach or something like that. So I'm going to describe a procedure for sort of abstract or extracting the statistics of this pattern. So what I'm going to do basically is just compute the correlations amongst all of the pixels in this pattern. So I can do this basically at any layer. So if I pick some layer within my network, and I'll have my filter map is of dimensions h and w, so height and width, but then I have so many channels that I've learned. So different filters I've learned at that layer. I start with that, and then I just basically take all of those channel-wise vectors and compute their outer products. And average them together. I'm getting what's called a graph matrix, which is used in computing things like correlation, covariance, things like that. Basically just this outer product is just basically the product of all of the different entries of the two vectors spread out in this matrix. That's called the graph matrix, and it's sort of encoding. It's encoding something about the relationships between pixels, between pairs of pixels all over this image. And what we expect is that something like that would actually capture the statistics of whatever periodic or mostly periodic pattern is appearing. It's efficient to compute. So So what do we do here? Well, let's take our pre-trained network and let's run inference. So we take our texture image or pattern image. Let's run it through here. And let's compute at each of these layers, let's compute these ground matrices. And then let's take just some random starting image like this. And let's use the same network and embed it. We're going to get probably some other, we're definitely getting some other activations. Let's compute their ground matrices. And then let's learn something that actually tries to minimize the distance between those two ground matrices. So we're actually training, we actually have like a new network. So like we use this pre-trained network to produce these ground matrices. And then let's take the difference between these ground matrices at the different levels. Let's use let's use some measure of their difference, in this case like L2 difference. And let's use that as a loss function where we can backpropagate that signal, the difference between those, to change again the original pixels of like the random image that we gave it. So again, it's something similar to what we've been doing in the past. But what we're trying to do here is instead of like matching like a gradient determined by the class of this thing or whatever activation, we're actually trying to like match up the statistics of the patterns within this original image. We're going to match that up and adjust the original image to have those same patterns. And what you see down here, which is not really awesome, but you can see that you basically you created like something kind of similar to it. From that random image, you adjust it and you get something that kind of, it's not the same image, but it has something like some similar statistical properties. Okay, so yeah, and you can do this. And you can do this matching up the statistics at any one of the layers. And like the point of this slide is making is like the higher up you go, the higher up in the network you go, like the more abstract layers, you get like these patterns that are capturing like larger scale correlations between like pixels within the original image. So great. So so what? Well, what's cool about this is that you can use this to. You can think about this as like a way of capturing like the artistic style within an image. So if I take either one of these images here and I look at the same these same outputs, I get something that sort of like looks like it's capturing something about like the style of what's in this image. I mean, this is loose, right? It's not like there's like some rigorous definition of style and this is it. It's just like, yeah, it seems to be that what I've captured out of here is not the content of what's in these paintings, but something about like how pixels relate to each other within this painting. And you can see they're very different from the two different styles. Okay, so what? Well, so what we can do then is we can actually train networks that learn to extract the content and the style of images separately. Thinking again, the style being like this ground matrix representation, and we can actually make images having one kind of content. We can actually make them have the other kind, like another kind of style, by making the ground matrices at the different layers from this image match with the ground matrices from different layers of this image. So again, those ground matrices don't say anything about the content; they just preserve. They say something about the style. And when you do that, you get something pretty amazing. I think is you get this original image. The original content is somewhat preserved. You see like buildings and this river, this walk. But you see that the style has completely changed. We now have like the swirling Van Gogh-like style in that. And that's pretty awesome actually. And you can go crazy with this. So this is like the details of what the network's like. You have a network again that's already pre-trained, like this AlexNet on ImageNet, and you have one image that is the style image, and you're computing these gram matrices, and you have a loss term matching up the gram matrices for your original random noise image there, and then you have you use the same network and produce what's called the feature or content loss, which is at a much higher level of abstraction, just trying to match the output from here, from these two networks here. And when you do that, you can sort of play with the balance of how much each of these different losses are weighted, but you get like this output image like we were just looking at. Yeah, so like this is like a depiction of different iterations as you do this. Like you start with a random image, and then as you do this iteration process, you get things that are more and more like the final product. So it's pretty cool to see that. You can do this basically with like any style. Again, the style here being like some image. And like I was saying, you can sort of like you can balance. So there's these weights that correspond to the losses of the style. You assign some weight to the loss to the content, and as you weight more towards the content, you see what you expect to see. You see like the original content being more obvious, and then as you increase the weights in the style, you see that going away, and you see more like what looks like the gram matrices themselves. So like that's pretty awesome. This is a slide saying that you can adjust the size of the input image, and this gives you slightly different types of style from the image. Yeah.
So this network just trains on one image?
Yes, it's the network. Yeah, so it is a network. You're not really training anything.
Just forward pass.
You're just using the gradients from existing networks. Yeah, so like you do have this you do have these new loss functions, but they're just immediately updated. I mean, they do back propagate through the network, but they're just immediately updating like the original input pixels like we've been seeing the whole time. So yes, so there really is no new network here. We're just using a pre-trained network, and we're using the different outputs, gram matrices from different layers, and the content output from a different layer, and then using those to back propagate on the random image. Yeah, you can like continue to take this even further. You can average different gram matrices to get like a mixture of styles. You can do all kinds of crazy things here. It is pretty slow. So there's this you actually do train a network. You can do this whole procedure like we were talking about to get to update this and get the image that you want. But then you can train another network to basically take you from the original image to the stylized image. And then once you have that, you can just forward propagate. Once you train that, you can forward propagate. So you have to have a bunch of examples of images at this point. You can then forward propagate any image through there, and you basically get the style transfer that you would get through this iterative process. That's pretty cool. Once you have that, then you can just basically go to town and stylize everything. And you can also make these conditional. You can make these conditioned on, so one network, many styles. So so remember how we talked about batch normalization and how it is a way of adapting the statistics of the network at any layer where you put the batch normalization. So you can take this further. You can actually learn. You can learn to condition the parameters of that normalization on the style. And so what happens is that you can instead of training a new network for every single style, you can train one network that's conditioned on the style coming in, and that adjusts the normalization parameters and therefore you can have one network basically producing many styles. So it just changed, like when you run inference, you give it the style image and it says, oh, okay, that means I should have different parameters in my normalization and my batch normalization. It's actually something called distance normalization, related to batch normalization, but just think batch normalization. And then I can stylize for basically all kinds of images. And there's like apps for this. I don't know if anybody's ever downloaded these things. I can't think what they're called.
Prisma.
What's that?
Prisma.
Yeah, that's right. Prism or Prism?
Prisma.
Prisma, yeah, Prisma, yeah. This is basically what Prisma is. Prisma is one of these conditional networks. And those networks, networks that are that you train to kind of do this, to learn the output of another network, can actually usually be made really small through a process called distillation. And so they put on your mobile phone, you run inference pretty fast, and all of a sudden you're stylizing your whole life. Every Instagram post you have is stylized. All your friends think you're really not cool. Except for your true friends. Your true friends think you're very cool. Yeah. So you're the end of it? No, not bad. I'm even good. I thought this was going to be right up against the end. Okay, so summary. So all kinds of crazy methods for thinking about what's going on in networks. Did any one of them really tell us what's going on in the network? The answer is no. But they do give us some better understanding of like what each of these, what different layers are learning, what each of the neurons in the layers might be learning, and maybe give us some understanding of like, how abstract features can be built up through the hierarchy of layers. So we race through all these different methods, and again, most of them are using gradients to produce new images that tell us something about like what's maximally activated for this neuron or whatever. So it's interesting, backpropagation and gradients, they're used to train these networks to solve these optimization problems, but they become useful again in trying to understand. And that's pretty cool. Because there are other techniques for training neural networks that are not gradient based. They're not nearly as well used as this, and you wouldn't get these byproducts of these kind of tools. So that's it. So I tuned you have 10 minutes of lecture. I did not realize it would go that fast. But yeah, there are lots of packages now available for like doing these things, and also just like apps for doing these things, and they're way fun to play with. Don't waste too much time, but anyway, we'll see you next Tuesday. And happy to answer any questions.
My brother has he's just starting out. No, he's a business professor, so it doesn't touch much very much. Just likes it.
That is exactly
Okay. No, I don't care. Sorry. Yeah. Okay. Maybe it's
Yeah, I'm gonna